All right, we've got our first question as the pulse rate of a population of Year 12 students are approximately normally distributed with a mean of 69 beats per minute and a standard deviation of 4 beats per minute. A student has a standardized pulse rate of Z equals negative 2.5. Now the question is asking us to find out what the student's actual pulse rate is. So we're trying to go from an actual pulse rate. So we're trying to go from a standardized pulse rate to the actual pulse rate. So the formula we want to use, we've got X, which is our actual pulse rate or actual score in the notes. X is equal to X bar, which is the mean, plus Z, our standardized score, multiplied by the standard deviation. We can just plug the numbers straight in here. So we've got X is equal to our mean of 69 plus, I'm going to put brackets here, negative 2.5, which is our standardized pulse rate, multiplied by a standard deviation of 4. So we get X is equal to 59 beats per minute. The next question uses the same set of data, but now it tells us that a student has a standardized pulse rate of Z equals negative 0.1, negative 1. The percentage of students with a pulse rate greater than this is closest to one of these answers. So the fact that the student has a standardized pulse rate of Z equals negative 1 means that his pulse rate is 1 standard deviation below the mean. Now we know from the bell curve charts in our notes that the percentage that lies below this point is 16%. If the entire bell curve is 100%, then everything that's shaded red here must be 100 minus 16, which equals 84%. So 84% of students have a pulse rate higher than that student. Next question again uses the same data. There were 200 students in total. The number of students with a pulse rate of less than 61 beats per minute or greater than 73 beats per minute is closest to what? So if we look at this graphically, again, let's draw our bell curve. So it wants to know, let's say if 61 is around here, we know our mean was 69 and the other number's 73. 73. So it's asking how many students were below 61 and above 73. So to work that out, we need to work out what these percentages are first. To do that, how many standard deviations from the mean is 61? Well, we've got 69, the standard deviation is 4. So 69 minus 4 is 65. Then if we minus 4 again, we get 61. So 61 is 2 standard deviations away. Now let's look at 73. Well, at 69, if we add a standard deviation, we get to 73. So 73 is 1 standard deviation away. Now in the chapter notes, we have a diagram that looks similar to this, which tells you the percentages below and above a certain point. So for example, we've got our point 61, which is 2 standard deviations below the mean, which is this point here. So this point will be our 61. And we want to know what percentage lies below this point. Well, below this point, 2.5%. For 73, it's 1 standard deviation above the mean. So this point here. Now, what percentage is above this point here? What's going to be 16%. So adding these two up, we get 2.5% plus 16%, which is 18.5%. So we need to know What is 18.5% of 200? (18.5% of 200) is 37. Equals 37 students.
Next question looks at the shape of this histogram. We've got most of our data to the left side, and it is skewed down towards the positive side. We've got a very long positive tail. So it is going to be positively skewed. So our options are positively skewed with no outliers or positively skewed with outliers. You can see as these ones are scattered out, especially this one all the way over here, I would definitely assume this one is an outlier. So our answer is going to be positively skewed with outliers, which is the right answer. Now we've got the range for this data set. What's the range? Well, if we look at the key, 4 with the 2 there represents 42. So for example, we've got 40 as our lowest number and 89 as our highest number. So the difference between 89 and 40 is 49. So our answer is going to be 49 as the range.
Next question asks, what is the interquartile range for this set of data? Two ways you can do it. You can do it by hand, where you notch off the highest, then lowest, then second highest, second lowest. Keep going till you find the median. Split it into two halves, find the median again to get your Q1 and Q3. Alternatively, you can let the calculator do the work for you. If you go into statistics and just enter all the data there, you can see we've got 40, then 41, 44, 44. We've entered them all. You just gotta be very careful that you do enter them all exactly correctly when you're doing it in the calculator. Otherwise, it's not going to turn out right. Once you've got your data set in, you can go calc, one variable, okay, and you get all your data here. Now, it doesn't give you the interquartile range, but what it does give you, it gives you Q1, which is 57, and it gives you Q3, which is 75. Now, we should remember that the interquartile range is the difference between Q3 and Q1. So it's going to be 75 minus 57, which is 18. Question 7 says, the time taken to travel between two regional cities is approximately normally distributed with a mean of 70 minutes and a standard deviation of 2 minutes. The percentage of travel times that are between 66 minutes and 72 minutes. So if we use the same method we did in question 3, let's figure out how many standard deviations below the mean 66 is. So we've got our mean of 70. Let's minus one standard deviation, we get 268. Let's minus another standard deviation, we get 266. So 66 is 2 standard deviations below the mean. Now, the mean plus 1 standard deviation is 72, and that's our other number. So that's 1 standard deviation above the mean. Question's asking us, what is the percentage of travel times that are between these two numbers? So again, if we look at this chart here, now we're trying to find out, here would be our 66, 2 standard deviations below the mean, and here would be our 72, 1 standard deviation above the mean. So in this question, we're asking what's the percentage that lies between these 2 points? One way we could do it is we could look at this point here and say, okay, everything below this point is 84%. But we don't actually care about this green bit. We only want this bit here. So we could say 84% minus this 2.5%. So 84% minus the 2.5%. And that will equal 81.5% of the data lies between these 2 points. Now there is an arguably even better diagram that is going to help us answer question 8. We have the volume of a cup of soup served by a machine is normally distributed with a mean of 240 mils and a standard deviation of 5 mils. A fast food store used this machine to serve 160 cups of soup. The number of these cups of soup that are expected to contain 230 mils of soup is closest to, well, if we use this diagram here, our mean is 240. Minus one standard deviation, 235, minus another standard deviation, 230. So this is where our 230 mils lies. We want to know the number of soups expected to contain less than 230 mils. So that's everything to the left of here. So this percentage here. To work out what percentage is below this point here, we can just add up these two percentages. We have 0.15% and 2.35%. Adding these together gives us 2.5%. So 2.5% of the cups of soup will have less than 230 mils of soup. But in total, there was 160 soups. So we need to know what is 2.5% of 160. So it's 2.5% of 164. So the answer is 4 cups of soup. Question 9 asks, what is the range of this data set? Now we should know that range is the maximum value minus the minimum value. So if we look through, the largest value looks to be 197 and the minimum value looks to be 125. So our range is going to be 72. Now we want to know what is the percentage of clusters in this sample that contains more than 170 eggs. Well, let's see how many values are more than 170. We've got 172, 192, and 197. So only 3 clusters out of the 12 are more than 170. So we want to make 3 over 12. We want to convert that to a percentage. To convert 3 over 12 over to a percentage, we just multiply it by 100. In your calculator, you're going to get 25. So 25% of this data set is above 170. In a large population of moths, the number of eggs per cluster is approximately normally distributed with a mean of 165 eggs and a standard deviation of 25 eggs. Using the 68, 95, 99.7% rule, let's determine the percentage of clusters expected to contain more than 140 eggs. So as usual, let's see where 140 lies with respect to the mean. We've got 165. Let's minus 1 standard deviation. We get to 140. So 140 is 1 standard deviation away from the mean. Now we want to know the percentage of clusters expected to contain more than 140 eggs. So this is where this graph is useful again. We've got our mean minus 1 standard deviation is the point we're looking at, and we want to know what percentage is greater than that. So above this point is 84%. So the answer is going to be 84%. Question 12 uses the same data, but this time we're going to know how many clusters are expected to have less than 215 eggs in a sample of 1,000. So let's see where 215 lies with respect to the mean. If we add 25 to the mean, we get 190. If we add 25 again, we get 215. So we know that 215 is 2 standard deviations above the mean. Looking at our chart here, we got 2 standard deviations above the mean. The percentage that lies below this point is 97.5. So 97.5%. So 97.5% will have less than 215 eggs. We have a sample of 1,000 clusters, so we want to know what 97.5% of 1,000 is. What is 97.5% of 1,000? It is 975. So we got our answer as 975. Question 13 again uses the same data. We have the standardized number of eggs in one cluster is given by z equals negative 2.4. And we want to know the actual number of eggs in the cluster. So we have the standardized number and we want to find the actual number. So we use the formula x, our actual number, is equal to the mean x bar plus our standardized score multiplied by the standard deviation. And we can just go ahead and plug the numbers in. So x is our mean of 165. We're adding our standardized score of negative 2.4 multiplied by the standard deviation of 25. Which is 105. And that is our answer.